First of all, happy New Year. It is my pleasure to present Francisco González from Mexico, who did his PhD in Cuernavaca about classical chaotic scattering. This was the work in which I was also involved. This is how we get to know each other. And then he moved to Bristol, to the University of Bristol, and to the School of Mathematics, where he entered into the study of quantum chaos, and now he is also involved in the study of the circadian cycle in plants. And now he will present an investigation closer to the origins, again a classical scattering problem, which was done in collaboration with Christoph Jung from Mexico and Florentino Borondo from Madrid. So please start.
Thank you very much for the invitation. First, I would like to explain the physical system. Imagine that we have a surface, a periodic surface, and this surface is oscillating with frequency. This is a permanent. Sorry. With a frequency omega, and this frequency represents the temperature of the surface. We consider one atom, and we send the atom, and the atom interacts with the surface in a complicated way, and finally, the atom escapes. The initial energy of the atom is this, and we consider an impact parameter plane. This is a periodic surface. Then the impact parameter plane, we can rescale and say that this length is 1. We measure the distance from one point. B. Okay. And well, we have final angle and a final energy, but for us it's convenient to consider difference of energy. This is the system. Well, this is a system with 2.5 degrees of freedom. I mean, to describe the motion of the particle, we need two coordinates, the distance, this distance, set, and the position here. Okay, and we are considering that the surface is oscillating. Then we need the time to describe the motion. For us, it's very convenient to consider an extra degree of freedom. That means that we associate to the time the extra degree of freedom, and then we have a dynamics in a 3 degree of freedom system. And this is convenient only for our description. Well, and well, here we have a plot, the cross section. What means that we put a detector here and measure which is the final angle. We measure how many particles arrives to this final angle and which is the energy, and we plot everything. Here we have the final angle and the change of the energy, and construct the histogram, and we have this nice picture. And the question is why we have this picture. And this kind of picture is a characteristic for systems with one open degree of freedom and two closed degree of freedoms. Which is our open degree of freedom is this set, and the closed degree of freedom, one degree of freedom is related with the periodicity of the surface, and the other closed degree of freedom is related with the oscillation of the surface. Okay. Well, this is the outline. First, I would like to explain some details about the dynamical systems, things very general. And after, we are going to see the procedure to study this kind of systems. The main idea is first try to understand the two degree of freedom system associated with the scattering. That means that we consider that the surface is static, and study with detail the scattering for this kind of systems. And after, with this information, we are able to understand the 3 degree of freedom system. Okay. Well, let me try to explain with detail this picture. Imagine that we have a system of differential equations defined in a 3-dimensional space, for example here, and we want to study the properties of this system of differential equations. And well, a very natural object that arises in the dynamical systems in this space, 3-dimensional space, the phase space, is a periodic orbit. Well, gamma. And a very good idea to study this periodic orbit is consider a plane to see the dynamics around this periodic orbit. This idea was developed by Poincaré 1 century ago, and is very useful if we try to understand the dynamics, because if we try to plot everything in the 3-dimensional space, it's not really easy to see the behavior of the things. Then Poincaré had the good idea and was, well, we can consider a plane transversal to the periodic orbit and see the dynamics on this plane. I mean, we take a trajectory near to the periodic orbit and see in which point on the plane we have an intersection. Then we have a map, a discrete map. And Poincaré developed techniques to study this kind of maps. Well, if we have a periodic orbit in the discrete map, we have associated with this periodic orbit a fixed point. And a very natural thing is try to understand the dynamics around this fixed point with the help of the linear approximation. Then for some special cases, associated with the linear matrix of this map, we have eigenvalues and eigenvectors. And for special cases, we have that the two eigenvectors, the two eigenvalues are real. Then we can plot the eigenvectors, and the eigenvectors taught us something really interesting. Let me try to plot here. Suppose that this is the map, this is the fixed point, and we plot the eigenvector, one eigenvector, and we plot the other eigenvector. Well, what tell us the eigenvectors? If we consider a point very close to the fixed point of the map, contained in the line defined by the eigenvector, and we apply the map, then we have that the margin of this point jump, but this jump is in the line, maybe here if the eigenvector is bigger than 1, and if the eigenvector lambda is minor than 1, the margin is closer to the fixed point. Okay, if we consider a small system, a small segment of points here on this line, and we apply the Poincaré map, we can see that we can construct a line, and this line has a very rich structure, and we can see here the structure. Here we have the hyperbolic fixed point. In this direction we have one eigenvector. In the other direction here we have another eigenvector. And we can see that the iterations form a line, but the line is really complicated. Poincaré was able to understand something about this structure, and he wrote that this structure is really complicated and contains an infinite number of intersections between these two lines, and the chaos is related with these structures. Okay, now some definitions. Well, an invariant set under the flow, I mean invariant under the set of differential equations. A point in this invariant set is a point such that if we apply the flow to this point, then this point is always in the invariant set. For example, if we consider the periodic orbit and we take the flow, this is always on the periodic orbit. The margin of the point is something very natural. But now with these lines, we have something more, a bit more complicated, but is the same idea. If we take a point on this line and we apply the Poincaré map, or the equivalent way, the flow, the iteration of this point are always contained in the red line, for example. And a very important point here is that the dimensions of these lines in the Poincaré map is dimension 1. Then these lines are barriers for the dynamics. I mean, the things that are in one side of the line are always in this side of the line. But I am going to explain with more details these things. Well, if the eigenvalues, if we consider the eigenvalue bigger than 1, we can see an expansion, and this expansion defines the green line, and the name for this line is unstable manifold. And if we consider the eigenvalue less than 1, we have a contraction, and this line is the stable manifold. Okay. Now we have another picture, similar, to see the connection between the dynamics and this topological structure. We consider points here between this segment of the stable manifold and this segment of the unstable manifold, and we consider the imaging of this region under the Poincaré map, and the imaging is this. That means that this level, this region, is mapped to this region. And we can continue and see what happened. Then if we construct the lines, the stable and unstable manifolds, we are able to see the dynamics. This is a key point. Of course, for Hamiltonian systems with 2 degrees of freedom, these stable and unstable manifolds arise naturally and divide the phase space in a natural way. But if we consider systems with higher dimension, sometimes the stable and unstable manifolds have other dimension and don't, is not the correct dimension to divide the phase space. Yeah.
Could you make some remarks about the stretching and the folding of the
yeah.
and its connection to chaos?
Yeah. Well, we can see here that the lobels, in one sense, are rotting here, and this is related with the expansion, the contraction associated with the hyperbolic fixed point. In one sense, this expansion and contractions generate the chaos and the mixing. Okay. Well, this is for systems with 2 degrees of freedom. Let's go to remember. For systems with 2 degrees of freedom, the phase space is for phi is 4 because we have two positions, two coordinates to describe the position of the particle, and we need another speeds to define the system. But we are considering Hamiltonian systems, then the energy is a conserved quantity, then we can reduce to a three-dimensional space and plot everything in this three-dimensional space. And it's possible to visualize and use these techniques. It's really simple. And well, the skeleton of the dynamics in this case are the hyperbolic periodic orbits, and the dimension of these hyperbolic periodic orbits is 1, and the stable and unstable manifolds of these hyperbolic periodic orbits is 2. Then is a natural barrier to divide the three-dimensional constant energies surface. This is for systems with 2 degrees of freedom. For systems with 3 degrees of freedom, we have 3 coordinates to describe the position of the particle, plus another 3 speeds, momentums, and the phase space has dimension 6, but if we consider systems with conservation of the energy, then we can consider a reduced space with 5 dimensions. The constant energy hypersurface has 5 dimensions. Exists a generalization of the periodic orbits, the hyperbolic periodic orbits, for this kind of systems, the normally hyperbolic invariant manifolds. And these objects have dimension 3, and the stable and unstable manifolds of these objects have dimension 4. Then it's possible to divide this 5-dimensional constant energy surface with the help of these invariant manifolds of the NIM, the normally hyperbolic invariant manifold. Okay. Well, here we have the model for the 2 degree of freedom system. Well, we have the momentum x, the momentum p, the potential. The potential is a Morse potential, very common in things related with scattering and these things. And well, okay. Now we consider many particles here with different value of the impact parameter, the initial position, and all these particles with the same momentum and the same energy, and we consider the scattering of these different particles. And what we can see? We can see that for very specific initial conditions, the particle never escape from the interaction region. And why we have this behavior? This behavior is related with the stable and unstable manifolds. That means that this particle start in a point here, and if we apply the Poincaré map is in this invariant line, that means that it's always in this line, but this line never this line well, the dynamics taught us that the particle is always around here. Yes, maybe it's a good idea to do a plot here. We consider the scattering function. What is a scattering function? A scattering function relates properties of the particle in the initial state, in the asymptotic region, and with quantities in the asymptotic region, but after all the complicated behavior. And you can see something like this. Complicate things, and for special points we have a singularity. That means that the particle, the final angle oscillates a lot. And if we approach to this point, we can see more and more oscillations. These oscillations are related with the structure of these stable and unstable manifolds. Okay. And here we have a plot.
We give the limit cycle. I understand there is a limit cycle here, or the particle can get across.
Limit cycle.
It oscillates on the surface. It just goes along the surface oscillating. Is that the limit cycle? The particle is in the stable manifold. This manifold is invariant under the flow. That means that if we take a point on this manifold and we consider the dynamics of this point, is always in the invariant set. In this case, is the stable manifold, and is trapped always. But what in the physically, which is the trajectory?
The trajectory, yes, is something.
Trapped on the surface.
Yeah.
Okay. So the particle can get trapped on the surface and just travel on the surface.
Yeah.
And then can have many rounds and then escape again.
Yeah. Okay. Here we have a plot of the singularities of the scattering function. This is the impact parameter plane. This is the initial energy. And we can see a structure here that is basically a Cantor set. If we cut this structure with a line, constant energy line, we can see a Cantor set. And this Cantor set is related with the structure of these stable and unstable manifolds. Okay. Do you have any question?
Upper left.
About what?
Upper left.
This plot? Well, this plot is a plot in color scale of the final angle theta as a function of the impact parameter plane and the initial angle phi. This angle is related with the degree of freedom associated with the oscillations of the surface. Yes, we are considering a 2 degree of freedom system, and then is independent of this angle phi. The system is not coupled. For this reason, we have the same value of the scattering function here.
for different values of the angle phi.
And how can we read off the positions of the singularities from this plot?
From this plot or
yes,
this?
Yes, on the left-hand side. Well, you have the interval of continuity.
Yes.
Maxima and
yeah. We have here, probably with best resolution is better. We can see here that the scattering function has regions of continuity and jumps. The jumps are related with these singularities of the scattering function. The scattering function is not defined for these values. And then we can relate, or in one sense read, the structure of the stable and unstable manifold with these singularities of the scattering function. And this is nice because we can understand the dynamics here only with information in the asymptotic region. That's the interesting point here. Okay, good. Well, if we change the value of the initial energy, we have a different structure for the stable and unstable manifold. Okay, this is for the 2 degree of freedom system. If we consider the 3 degree of freedom system, what we can do? The first step is consider the 3 degree of freedom system, but when the coupling between the oscillation of the surface and the other 2 degrees of freedom is 0. It's a good point to start. Then we can consider the Poincaré map associated with this 3 degree of freedom system, and to construct, we can construct a stack with these Poincaré maps associated with the 2 degree of freedom system. And if we take the union of all the stable and unstable manifolds parameterized by the energy, and we consider the Cartesian product with the cycle represents the oscillation of the surface, we can construct the stable and unstable manifold for the 3 degree of freedom system. And a nice property about these objects, this stable and unstable manifold, is that are robust under perturbations. That means that if we couple the oscillation of the surface with the other 2 degrees of freedom, probably the structure is deformed, but the surface, the hypersurface, exists. It's not destroyed. And okay. And this property is very general. I mean, doesn't matter which is the way that we consider to couple the oscillation of the surface with the other 2 degrees of freedom. This kind of structure is robust and very general. Well, here we have the 3 degree of freedom system associated. We consider in addition this momentum and this extra coordinate that represent the oscillation of the surface, the position of the oscillation. And well, this is the Hamiltonian. And this parameter B is a a parameter to couple the 3 degrees of freedom. Okay. Well, now let's see what happened with the scattering function for the perturbed system. Well, for the final angle theta, we can see that the lines here are well changed, and we can see more structures here. We can see annulus and a hole here. I mean, the regions of continuity for the perturbed system are have different topology because we have now annulus here, and here we don't have the same kind of annulus, and we have the small disk here, and here we don't have the small disk. And which is the origin of this structure? Why we have this kind of lines? Well, if we think in the stable and unstable manifolds, and these manifolds are robust under perturbations, that means that when we perturb the system, these hypersurface are deformed, but in one sense we have the same lines, but it is something like consider this figure and deform the figure, deform the lines, and take a line here and see. And for example, here if we consider a point here and we deform these lines, then the maximum is maybe here. And if we cut with an horizontal line, now we can see more things. But other possibility is that the deformation is something like this. We have two maximums, and if we cut with one line here, this minimum generate the hole here, the small circle. Okay. Any questions?
One observation. The variable that you denoted by phi here was denoted by psi.
Yes. Thank you very much.
So this coordinate that corresponds to a third degree of freedom, and is conserved.
Sorry.
Okay, not conserved. Yeah.
No.
Conjugate variable is conserved. Yeah. Yeah. If there is no coupling, and this is why this is the difference between the upper line of plots and the lower line of plots. Yeah.
Okay.
I have something I don't know. A few things I understand. First, you're using a formula which is Hamiltonian system.
Yeah.
So energy is conserved.
The total energy, yes.
So, and there is a single particle.
Yes, but
So where the energy goes when there is a delta energy here?
well, the 3 degree of freedom system consider the surface plus the particle. That's the trick.
So the energy goes to the surface.
So it's oscillating, right?
But and if it is oscillating in time, in the previous potential that you plot, where is the time? Where is the time here?
Is here. C is T.
Phi is
Yeah.
So because it's a non-autonomous system that it has converted to autonomous and using
Yeah.
But then the number of variables that you counted at the beginning is not correct, because you have to add a new variable. You say 3 degrees of freedom, 3 coordinates, 6 degrees of freedom, are 6 plus 1.
No, please.
It's a 7-dimensional dynamical system because there is time.
The time is considering this extra degree of freedom.
Right, so there's 1 other degree of freedom.
Here we have 1, 2, and if we consider the position C, 3.
So for what? For
3.
For x and z, there is x, z, dx, dz, and t, 5.
Ah, okay. For me, degree of freedom means the coordinate that I need to describe the position.
The dynamical system is 2n plus 1.
No. Here we have 1, 2, 3, 4, and here time 5, and that's all.
That's a 5.
Yeah, that's all.
Now the other question is, in these results that you get, what is the dependence on the, which is not clear to me, what is the dependence on the wave vector on the spatial modulation? The dependence on the capital J, which is the wavefront.
This?
J over A, which is basically the wavefront. So what is the dependence on the wavefront? I guess that the result should be very different if the wavefront of the spatial modulation is small or is big.
Yeah, yeah.
It's not clear to me what is the dependence on that. Because we focus on the dependence on the energy of the initial and angle, but to me the shape of the surface should give a big dependence on that.
Yeah, yeah. The important point here is that we are consider topological structures in the phase space. We take these values because someone, Florentino, has very good experience with this potential, and of course the caustics and the tails are connected with this function, but the explanation why we have these structures for the caustics is the same, because the explanation doesn't depend about the details, only that is a closed degree of freedom. That's an important point.
So A, the capital A doesn't matter.
This?
Is the period of the period of the psi variable. It's just the size of the angular variable psi. That's it.
Okay. Thank you.
And Jason integers, so
Yeah, no, the integers is because you have harmonics there, but I don't understand that especially degree of freedom. No. Because probably the point that I guess the particle is point light. I think I'm just scared right now.
You do not have vertical coordinates, you do not have any y coordinates. The 2 degrees of freedom system is flat, and the 3rd degree of freedom is introduced by the time dependence.
The oscillation. Of course, we can consider the scattering in
a plane.
Yes, in a plane. But it's the same idea, I think, if the potential is periodic in the 2 directions. It's the same idea. Okay. Here, okay, exists a nice interpretation that connects the graph, the plot of the scattering function with the cross section, and the explanation is simple. We consider the plot of the scattering function. Then is a plot in a 4-dimensional space because the domain is 2-dimension and the contra-domain is 2-dimension. Then we plot everything in a 4-dimensional space. And if we project this this plot on the plane of
the contra domain, we have the structure of the caustics. Well, in a function, we have domain and contra domain.
In the particular
In the setup,
variable defined.
yeah, the domain is defined by the initial angle phi and the impact parameter, and the contra domain is defined by the change of the energy and the final angle. Yeah, and here we have a kind of sketch. For example, if we consider this idea, but with in a 30-degree plot, we have this thing, and if we project this plot in a plane, we can see this, and we have the caustics here, these structures here, and for our system, we have something very similar, only in more dimensions. That's all. And for this reason, we have this structure like rosca de reyes. We have a hole in the center, and well, we can see the caustics, and another rosca de reyes here, but it's more clear. This is a small one, and well, exists a well, if we change the value of the initial energy, we have different structures for the caustics, and is connected with the structures in the scattering functions. Okay, well. Well, to study the 3-degree of freedom system, we start with the 2-degree of freedom system. Is convenient because we understand very well the dynamics and the structures in the 2-degree of freedom systems. Then we can use this information and the property that these stable and unstable manifolds are reduced under perturbations and are natural barriers to divide the phase space. And we have a connection between the structure of the singularities of the scattering function with the structure of the caustics. Yeah. And, thank you very much for your attention.
Thank you for the talk, and now we have time for questions. Emilio.
You say you have related this variation of the surface to some temperature. Well, I would say it's not the same. A temperature and a frequency is, and you have called the bifrequency. The bifrequency is the maximum frequency of a set of forms. So I don't understand. Well, I understand that qualitatively you are moving something, and temperature is also moving something. But there is some quantitative relationship between this frequency and some temperature. Is comes from some experiment or from some theory? Or is just both things are moving related to motion?
Yeah, Florentino told me that it's related with the Debye frequency, but I don't have more details. I'm going to ask to Florentino.
More questions?
Sorry, what is the physical meaning of the caustics in your problem?
The physical meaning, well, an important point here is that, well, if we put our detector and count the number of particles that arrives at this point, we can see that in the caustics we have an accumulations, and it's really easy to detect the particles if we have acoustics.
you are going to have a high intensity signal in the detector placed at that position. Further questions? If no, then let us thank the speaker.